Hello, my name is Alexander Battig. I am a chemist and a material scientist working in the group of Dr. Bernhard Scharte at BAM. And my talk today is titled Sustainability and Flame Retardancy, Bioeconomy, Fire Science, Future. And I'd like to begin actually by talking about the future. You know, as scientists, we're always eager to see data and try to see different types of trends. So let's look at where we are and where it is that we are going. You know, just this year, record-breaking temperatures swept across Europe. Particularly, the south of France saw severe droughts, and in Germany, the River Rhine ran so shallow that ship transport wasn't even possible at times. We saw wildfires ravage Brandenburg and Saxony, and in Portugal, temperatures of up to 44 degrees Celsius were measured. Similar trends were seen all throughout the continent, and it's not just Europe, it's all over the world. In Pakistan, we saw severe floodings with as much of a third of the country's surface covered in water. Just a few years ago, severe wildfires swept across Australia. And these changes, they highlight not only a change to local weather, but also a drastic shift in global climates. When we look at global surface temperatures from satellites, we see that there's a change across the years. We see a shift to increasing surface temperatures, and most research institutes they agree that by 2025 we should see a change in global temperatures versus the normal of about 1 degree Celsius. You know, one of the driving forces for these changes in climate is what some refer to as the anthropocene, or the human epoch. It's the relationship between the geosphere on the one hand and the anthroposphere on the other hand. This is our political economy, our human culture, but also the way that we use and consume different materials from the environment. It's our use of these resources that have a direct influence on the geosphere by creating pollutants that seep into soils and waters, and greenhouse gases that drive climate change. If we're to solve some of the issues, then we need to take a closer look at improving exactly how we extract resources from nature, and especially how we reduce pollutants and move away from fossil fuels. One way of thinking about how we can achieve a more sustainable society is by not thinking of our economy really only as a one-way road with respect to resources. One of the alternatives is to establish what some people call a bioeconomy. This involves using well what we don't use yet, but it also involves using better what we already use. The bioeconomy aims at producing, developing, and using biological resources, processes, and systems with the aim of supplying products, processes, and services to all economic sectors to secure a sustainable economy. One way of doing that is by strengthening circular economies through evidence-based research of biogenic resources. And at BAM, establishing and utilizing circular economies play a major role in our research. And particularly, many of them look at the material input and the reuse of waste. That seemed clear to you exactly how flame retardancy and bioeconomy really fit together, but I hope to show you that there is actually a great chance for sustainability and flame retardancy to achieve goals related to the bioeconomy. Now, flame retardancy is obviously just one of the aspects to a larger idea when it comes to material science and safety. And BAM focuses on fire science to investigate different kinds of fire scenarios, like fires in buildings or outdoor fires, and several multi-connected topics like detection, monitoring, and surveillance, simulation and machine learning, and critical infrastructure. Okay, so what is flame retardancy and really why is it important? Well, most polymers are made of hydrocarbons and contain some functional groups. Most polymers are very flammable. Some would even say that they're sliceable petroleum. So to make sure that they can be handled safely, you use flame retardants. So what I'm showing you here is a typical temperature curve over time of a room fire. So what you have is an incipient stage where the fire starts, and then a developing stage with a sharp increase in temperature during the flashover, and finally the entire room is on fire. Well, flame retardants work by preventing ignition in the incipient stage or by reducing flame spread in the developing stage. When polymers burn, the pyrolytic decomposition fuels the flame in the gas phase. Combustible gases react with oxygen in the flame, and the formation of combustion products is exothermic, which cause a thermal feedback loop that drives further decomposition. So flame retardants, and especially phosphorus flame retardants, they work by either promoting char in the condensed phase or by flame inhibition in the gas phase, where phosphorus works via radical scavenging. Now, one way to lower the danger of fires when it comes to polymers is to use less polymers. And that's exactly where composites play a large role. You just replace the fuel with something that doesn't burn as well and that also changes the material properties. In a recent publication, these authors outlined different types of biocomposites in a very interesting way. They show that there's many different types of biocomposites actually. There's biocomposites where you have synthetic polymers combined with natural fibers. You have natural polymers combined with synthetic fibers, but very green biocomposites are combinations of natural fibers and natural polymers. So what are natural fibers and natural polymers that are used in composites? Well, one of the most common types of fillers are plant-based fillers. These include sisal and kenaf fibers. And one of the most talked about biopolymers actually is polylactic acid. So polylactic acid is formed from, as the name implies, lactic acid. And what you create is a bio-based polymer from a monomer that is usually grown from, or rather harvested from corn. Now this brings its own difficulties with it, but I'll get more into that in just a few moments. Now, when it comes to the flame retardancy of polylactic acid, there's also been a significant amount of research already done on this topic. Here are some fantastic reviews from some great authors you can look at on your own time. Also, our working group has been working on polylactic acid biocomposites using a green flame retardant filler and polylactic acid, of course. But just very recently, what was also done is these authors used polylactic acid bead foams to create an intrinsic flame retardancy of the material. It's very fascinating. Now, when it comes to PLA or some other components, as I mentioned, PLA comes from corn, but it's not just PLA. It's lots of other compounds that are used for the polymer industry, fillers and things like that. You really have to think about, well, where do these materials come from ultimately? And in English, there's a word to describe this phenomenon, this competition that takes place. It's called fuel versus food, right? So the idea is that you can either use the corn to feed someone, or you can use the corn to create biofuels. But this fuel versus food, it's not quite as nuanced because not everything is fuel per se. So I like actually the German word for it much better. And that German word is Flächenkonkurrenz. It means a competition for space or for area, because ultimately that's what it boils down to. You have a set amount of space and you have resources that you can grow on it, and it's a question of exactly what resources you should be using for what area. Now, we need to really rethink of how we use those resources. What we should be doing is utilizing available resources more strongly and reusing, repurposing, or upcycling a lot of materials, and really rethinking exactly what we know as waste. After all, it was Buckminster Fuller, the architect, who said, Pollution is nothing but resources we're not harvesting. We allow them to disperse because we've been ignorant of their value. Well, a lot of authors have not been ignorant of the value of waste per se. And what that's led to is a surge of bio-based approaches when it comes to flame retardancy. Some of them I'd like to mention here, particularly the works concerning using tartaric acid as a bio-based flame retardant, or derivatives of tartaric acid as a byproduct of the wine industry. Also using isosorbide, phosphorylated isosorbide derivatives. Also using gallic acid, so you see that there's these naturally occurring building blocks that can be used, phosphorylated, and in some way functionalized, that they can be used as flame retardants. Also, there are bio-based chemicals that already contain phosphorus that can also be used as flame retardant fillers or compounds in polymers, for instance in polyesters and in epoxy resins. There's also been interesting use of eugenol as a biogenic building block for these materials. Also investigating soybean oil and functionalizing soybean oil as a type of material in these biocomposites, and as well as sugar-based bioepoxy resins. So you see there's a lot of research on bio-based approaches to flame retardancy. Some of them involve adding compounds into the material that is bio-based. Others are more based on using building blocks that are integrated into the polymer backbone that are bio-based. One of the research routes that I myself have been involved in involves these so-called non-vegan fillers. So these are fillers that are not based on plants, but they actually come from animal byproducts. So some of these byproducts are, for instance, keratin and chitin. Collagen has been investigated, casein, but also DNA, particularly DNA, has a very interesting flame retardant property. And what combines these materials actually is that biomass naturally incorporates nitrogen and phosphorus, and these compounds are extremely important for a halogen-free flame retardancy. Now, one of the works I'd like to talk to you about now is actually one of my own works. The idea here was that in cooperation with a scientist from Mexico, what we investigated was using leather waste as an additive to polymers. Now, the idea of where does this leather waste come from? Well, when you have leather, a natural product, what happens is that the flesh side is normally carved off, and this scraping, these leather scrapings, they're essentially garbage. They're just thrown out. They're landfill. They have no further purpose. And so the idea that this scientist had was, what if we actually harvested this material and investigated it as a flame retardant compound? Well, what we eventually found out is, well, the leather compound is mainly made of collagen, and this collagen compound actually interacts with phosphorus flame retardants in a polymer, in this case EVA. This is polyethyl vinyl acetate. It's a type of cable material. The leather waste and the flame retardant additive, they actually combined, they synergized in this material to create a really thick char layer, to reduce the fire load, to reduce the heat release with respect to time. So there was a really successful way of implementing waste as an additive to polymers. So the previous research that I showed you was actually quite interesting in the way that we saw that using leather waste in polymers has some synergistic effect. And we took it one step further in the next few works that I'd like to share with you right now. The basis of it was that we knew that the European Union approved insects as a novel food in the European Union. This includes the migratory locust, the house cricket, the yellow mealworm, and black soldier fly as well. And these insect types are not just used as a food for humans to fill our demand for proteins, but also as a food source for fish and for poultry and for pigs. So there's a huge market that is suddenly expanding when it comes to these insects. And that also means that there is a huge market that could be available for potentially flame retardant compounds from insects. So that's exactly what we investigated in our non-vegan paper. These insect fillers using black soldier fly, using house crickets, but also using bone meal and eggshells as bio-based fillers for epoxy resins using phosphorus flame retardants. That was our goal in this paper. And what we saw is that there's actually a synergistic effect between these two. We quantified the synergy, but we saw that there was a lowering of fire load. We saw a synergistic reduction of the maximum average rate of heat emission. So there's a slowing down of the fire when you add these compounds because they don't burn quite as well. And moreover, more importantly, they interact with phosphorus and phosphorus-based flame retardants to really create a very thick char layer and reduce the total heat evolved of the material. And in another work, we investigated the yellow mealworm, so the mealworm beetle, but also the larva and also different compounds from it, fats, chitin, etc. And we wanted to really investigate which of these compounds interact with different types of flame retardants, one in the condensed phase active, one of them that's active in the gas phase. And we combined these into a tannic acid-based epoxy resin to make a more sustainable material and show as a proof of principle that specific compounds in these insects are actually creating a flame retardant effect on epoxy resins. Moving on, a different type of approach that we used to investigate other types of biogenic based fillers was using what's known as biochar. We used two different types of biochar. One from cocoa shell and the other one from what we called autobahn char. Essentially, this is a wood char that is produced from the shavings from the side of the road. So whenever you see these construction cars driving by the autobahn, shaving off the grass and the weeds on the side, this material was captured and then pyrolyzed to create a strong wood char we called autobahn char. Well, this material was combined with kenaf fibers and also with cyclodextrines in biosourced epoxy resins. And some interesting things happened here. What we saw was that by using our different types of fillers, you see a reduction of the heat release rate with respect to time compared to an unfilled material. So the black line, what I'm showing you here is the heat release rate as a function of time. The black curve is the pure green epoxy resin, and the blue lines are just flame retardant compounds, and the red lines are combinations of our biochar and our flame retardants. And you'll note that the shape of the curve changes significantly, and that's because we're creating a very thick char layer. The char is actually protecting the material, the underlying material from the fire, from the heat on the top. And it works actually really well, particularly when you use cyclodextrines. However, there is still some fine-tuning to be done. The results also show that this material can expand in volume very, very rapidly. And so it's an ongoing project, to say the least. So it's not just epoxy resins that we investigate, but we also did research on foam structures, particularly using phosphorylated soybean oil and expandable graphite in flexible polyurethane foams. And what I'm showing you here is a pure flexible polyurethane foam with different increasing amounts of phosphorylated soybean oil. Now, the soybean oil was used as as a diol, as a functional diol in flexible polyurethane foam. So that means it was used as a building block inside the material, and it didn't have the strong effect that we really were looking for. However, when it was combined with expandable graphite, something really unique and interesting happened. And as you see here, with increasing expandable, well, by keeping actually the expandable graphite content constant at 10 weight%, we see a drastic increase in residue, and the morphology of the sample changed completely after fire. So what you see here is a scanning electron microscopy image, and you can very clearly see this expanded graphite material that is being glued together by this phosphorus residue. So again, there you see an interaction of this bio-based compound with another flame retardant additive inside different types of materials. Now, finally, I'd like to talk to you about some of our current research, or rather some of the research that we've just started on, some of the topics that we are pursuing at BAM and in the work of working group of Professor Dr. Bernhard Schate. One of them involves using phosphorus-rich algae as a flame retardant filler for biopolymers. So the idea here is to use algae as a sort of sponge because it contains a lot of phosphorus, and then using it as a flame retardant for biopolymers. Another work focuses on using or flame retarding polylimonene carbonate using bio-based materials as well. So if you don't know what polylimonene carbonate is yet, it's a type of polymer that's based on limonene, and limonene is a compound that is extracted from lemons, and the production of polylimonene carbonate actually consumes carbon dioxide. This is done with a catalyst, but it's done at room temperature at 24 degrees, but at 25 bars. But it is technically possible to create this material. It's a bio-based material. It has some unique material properties, and investigating the flame retardancy of this material is one of our new topics. What I've tried to show you over the last couple of minutes is that certainly there is a space for sustainability in flame retardancy, and that has a lot to do with the bioeconomy. So the bioeconomy is one way of really moving towards a more sustainable society, reusing waste, reusing or reimagining the way that we use materials. And the bioeconomy also fuels research into material science, because we need cutting-edge technology, new types of materials if we want to solve tomorrow's problems. And of course, flame retardancy and material safety plays a huge role in material science. So I hope I've been able to show you that they really do belong together. We don't have to continue consuming our resources in the way that we've done before. There's still sufficient time to change our course. I'd like to leave you with some food for thought now, and that is a quote by Leonard Bernstein, who said, "To achieve great things, two things are needed: a plan and not quite enough time." Well, we don't quite have enough time, the way our climate is changing, but we do have a great plan, and so maybe, just maybe, we will achieve great things. Thank you for your kind attention, for your interest today, and if you have any other further questions, let me know. My email is here. Thanks so much. All the best.